Hi, this is Tzvi Rosen with the last formal lecture in our series on algebra and geometry. In this lecture, we will state and elucidate Bézout's theorem, and then make our way back to ancient Greece with Pappus's theorem. Let's get started. So we've spent a lot of time working through some background for Bézout's theorem. We talked about projective geometry. We talked about intersection multiplicity. So now we're ready to state Bézout's theorem, and we'll go through it a piece at a time. But first, here's the statement. Let C and D be curves in the complex projective plane with no common components, and let M and N be the degrees of their reduced defining equations. Then the sum over the points P in the intersection C and intersection of C and D of IP of CD is equal to the product M times N, where IP of CD is the intersection multiplicity at P. And this is the statement from Ideals, Varieties, and Algorithms by Cox, Little, and O'Shea, which is a really great textbook I recommend. So we're going to take this theorem a piece at a time and explain why each piece is necessary. The first piece is complex. Why is it necessary that we're working over the complex projective plane as opposed to, for instance, the real projective plane? Well, let's consider the following example to understand this. So let's say we have the two curves C given by x squared plus y squared equals 1, and D given by x plus y equals 4. Then our graph would look something like this. We would have a circle of radius 1 at the origin, and then we would have a line passing above and to the left of it, to the right of it. Okay, so these two will never meet, at least not over the real numbers. But we can try and solve over the complex numbers just algebraically. So we can take, for instance, from D, we can take y is equal to 4 minus x and then sub it into C. And we'll get x squared plus 4 minus x quantity squared equals 1. And this is equivalent to x squared plus 16 minus 8x plus x squared equals 1. Okay. And gathering these terms together, we'll get 2x squared minus 8x plus 15 equals 0. And now we have a familiar quadratic equation, which we can solve using, for instance, the quadratic formula. So we know it's 2x squared minus 8x plus 15 equals 0. So that means that x equals, 8 plus or minus the square root of 8 squared, or 64, minus 4ac, so 4 times 15 times 2, all over 2a, which is 2 times 2. So that means x is equal to 2, after you divide out by 4, plus or minus a quarter of square root of 56. Okay, after you do the math on the inside here. Sorry, it should be minus 56. And then we get 2. We can factor out factor 4 from 56. So it's 14 times 4. So we'll get 2 plus or minus. That becomes a 2 after taking it out of the square root. So we get a half. 1/2 square root of minus 14. Okay, when you have a square root of a negative number, then in complex land, that can be thought of as I times the square root of a positive number. So So this is going to be 2 plus or minus I times the square root of 14 over 2. Okay? And now to get the corresponding y values, you just take y equals 4 minus x. Okay, so our solutions, after all that, are x equals 2 plus I times the square root of 14 over 2, and 2 minus I times the square root of 14 over 2 when you subtract it from 4, and 2 minus I times the square root of 14 over 2, 2 plus I times the square root of 14 over 2. And it makes sense that we get versions where you swap coordinates because both equations were symmetric in x and y. Okay, so looking back at this example, we found that over complex land we have two solutions, which is exactly what you would expect from Bézout, since one equation had degree 2 and one equation had degree 1. Using the Bézout theorem, so 2 times 1 is 2, so you should have two solutions, but we needed to move into complex land in order to do that, because there's no real solutions to this equation. But we have complex solutions, so we are in good shape. Okay, moving on in the statement of the theorem. Let C and D be curves in the complex projective plane. So this has to do with the problem of parallel lines that we discussed in the projective geometry lecture. So an example where we wouldn't have an intersection that we need would be if you have x plus y equals 2 and x plus y equals 1, then C intersect D will be empty. There's no pair of points x, y, there's no pair of values x, y where x plus y is both equal to 1 and to 2. Okay? But over the projective plane, so then we switch to homogeneous coordinates. So we're looking at points x, y, z satisfying, and then we take the homogenized versions of these equations. So you have C gives x plus y equals 2z, and D will be x plus y equals z. Okay, and here we can find a point in common. So to take C with x plus y equals 2z and D with x plus y equals z. So all you need to do is subtract the two equations to find z equals 0. Okay. And once you have z equals 0, then you're left with x plus y equals 0. So an example of homogeneous coordinates that would fit this equation is (1 minus 1, 0). And indeed, any other pair of representatives would be describing the same point in projective space, remembering that whenever you scale a point in projective space, the homogeneous coordinates, you're still talking about the same point. So this is the unique solution point, and we needed to move into homogeneous coordinates over the projective plane to solve it. Okay, moving along, we have with no common components. And what's the problem here? Well, we're worried about the following situation. What if I tell you one of my curves is x plus y equals, or rather, x plus y times x minus y equals 0, and my other curve is x plus y times x squared plus y squared minus 1 equals 0. Okay, well, the curves that we're describing would be, for C, we would get a pair of lines. Okay, so that would be our C. As for D, we would get the line x plus y equals 0. Okay, because that on this second equation is always satisfied if x plus y is 0, because then you have 0 times something else equals 0. On the other hand, the second factor, x squared plus y squared minus 1, that's 0 exactly on a circle of radius 1 centered at the origin. So how do these curves intersect? Well, as you can see, there are infinitely many points in the intersection. Oops. Because there's a whole line here. Okay? So in order for the results of Bézout's theorem to apply, you need to make sure that there are no common components, in the sense of a line which sits in both curves. Okay? Okay. How about reduced? So the idea here is we don't want an equation which has redundant factors. So for instance, I could have x plus y to the 10th power equals 0, and x minus y to the 5th equals 0. And in terms of the graphs of these two equations, let's say this is C and this is D. In terms of the graphs, we're really looking at two lines. Okay, that's the line corresponding to x plus y equals 0. That's C. And then to get D, we take x minus y equals 0. So really, it's a pair of lines, but Bézout's theorem would tell us that there should be 50 intersection points. Okay, so that's what you would get if you were to take the product of the degrees. So you can address this using tools like intersection multiplicity, but Cox-Liddell and O'Shea choose to require that these are reduced. So reduced means that we don't let powers like this. No powers of defining equations. Okay. And finally, we have intersection multiplicity, and we've spoken about this at length, but just as a reminder, we could have x minus 1 squared plus y squared equals 1, and x minus 2 squared plus y squared equals 4. And this would be describing two circles So one of them of radius 1 hitting the origin, and one of them of radius 2. Oops. Okay, and they would be tangent at the origin. And that's why we need this intersection multiplicity, to make sure that this tangency captures the fact that there's really more than one intersection point located at the point of tangency. So really, there should be two intersection points counted at the origin due to tangency. Okay, and a way to convince yourself of that is if you were to shift this circle just a little bit, then we would find that there are now two intersection points here and here. So the fact that when you move it to a point of tangency, you get a single point, we should figure out from that there's really 2 points hidden in that one. Okay, so that covers all of the points in this theorem. We're saying that if you account for all of these factors, you have to include complex numbers, you have to be working over the projective plane, the two curves can't have any common components, and you have to count with intersection multiplicity, then Bézout's theorem is satisfied. You have that the sum of the intersection multiplicities is equal to m times n. Let's see how this works in practice. So we have a curve C, which is defined by x squared minus y plus 2 squared equals 1, and D, which is defined by x minus 1 squared minus y plus 2 squared equals 4. So we can see that these are two hyperbolas, and just based on degree alone, we can determine from Bézout that there should be 2 times 2, or 4, intersection points, because each of the curves has degree 2. So now let's see a graph of these curves to know what we're dealing with. Okay, so curve C, hyperbola centered at 0, minus 2. Okay, apologies for the quality of my drawing. And curve D is centered at 1, minus 2, but it's stretched out a bit so that you get this. Let's see if I can do this a little better. Oh, it should be like this. Okay, there should be a tangency here, and then we get this part of the curve here. Okay, you'll pardon the quality of the drawing, but the general point should be apparent that in terms of real intersection points, this is it. It's the point minus 1, minus 2. Okay. And so when we have only one intersection point, but we're supposed to have 4, that should tell us something is wrong. But we know that we're not accounting for everything yet, right? We're not accounting for complex, we're not accounting for projective, and we're also not accounting for intersection multiplicity. So the first thing is that this has intersection multiplicity at least 2 because it's tangent. Okay. As for where the other intersections are, for that, we want to use one of our tools for calculating intersection multiplicity. So we're going to the first thing we're going to do is to homogenize and see if we can understand what our solutions will look like. So we have x squared minus y plus 2 squared equals 1. That becomes z squared. Okay, and y plus 2 squared should be y plus 2z squared. As for the second equation, it's x minus 1. That becomes x minus z squared plus, minus y plus 2z squared equals 4z squared. Okay, so these are the homogenized versions of our equations. Okay, now let's simplify. So this is our c and this is our d. So for c, we'll get x squared minus y squared minus 4yz minus 4z squared equals z squared. So I'm going to just subtract that over to the other side, and this becomes 5z squared equals 0. Okay, d gives us x squared minus 2xz plus z squared minus y squared minus 4yz minus 4z squared equals 4z squared. So to get everything on one side, I'm going to take this 4z squared and combine it with this one and get minus 8z squared equals 0. But I also have this z squared term, so I'm going to cross this out. This becomes 7. Okay. And now, if you remember how we compute intersection multiplicity, we want to express each of these as polynomials in z. Okay? So c, we want to take first the highest degree z term. We get minus 5z squared. Then the next highest is minus 4yz, because we've got a degree 1z term. And then the remaining is x squared minus y squared. Okay. As for the second equation, again, we're grouping things according to the degree in z. So we have minus 7z squared. Okay, and then we get minus 2x minus 4y, and let's just group them. We'll call this plus minus 2x minus 4y z. And finally, x squared minus y squared. Okay? So taking these two equations, we can use the intersection multiplicity approach. Sorry, we can use the resultant approach to compute the intersections here. So in order to do that, we take the resultant with respect to z of the two defining equations. So we'll start with the, and again, so it's degree 2 both of them, so we'll have 2 lines for each equation. And so we take minus 5 minus 4y, x squared minus y squared, and then we shift it forward 1, minus 5 minus 4y, x squared minus y squared. And then we get minus 7 minus 2x minus 4y, x squared minus y squared, minus 7 minus 2x minus 4y, x squared minus y squared. Okay. And now we're going to try and compute this determinant. Now, row operations don't change the determinant. So I can add minus row 4 to row 2, sorry. You know, actually, let's do it the other way. Why not? And also minus row 1 to row 3. Okay? And what we get, I'll do on the next page. Okay, we get, so the first 2 rows are unchanged. minus 5 minus 4y, x squared minus y squared, minus 5 minus 4y, x squared minus y squared. But then the next two rows change a lot. You get minus 2, and then the 4y's cancels, so we have minus 2x. X squared minus y squared cancels altogether, 0, 0. And then the same in the next row, minus 2 minus 2x, 0, 0. Okay. And so from there, we can try and do the calculation. Oh, you know what? Let's do one more of these. No, yeah. Let's just go ahead and do the calculation. So we'll try and take it along. Let's say column 1. So we're going to expand along column 1. So we have minus 5 times minus 4y, x squared minus y squared. Sorry, no, we don't get that. Just like this, minus 5 minus 4y, x squared minus y squared, minus 2x, 0, 0, minus 2 minus 2x, 0. Okay, but this determinant is really easy because there's only one product that doesn't vanish, and that's minus 2x times x squared minus y squared. And we'll write that down in a moment. So we have minus 2 times minus 4y, x squared minus y squared, 0, minus 5 minus 4y, x squared minus y squared, minus 2 minus 2x, 0. Okay, now let's bring that to the next page. Okay, so as we said, this one's relatively easy. We get minus 5 times, well, we pick up a minus sign because we're taking it, actually, this one is, so the minuses will cancel actually. So we'll just take the product. So it'll be minus 2x times minus 2x times x squared minus y squared. And then here we get minus 2 times, well, we can expand on the third column. So we just have the last thing. So it's x squared minus y squared times the, and we'll probably pick up a minus sign there. So let's keep that in mind. This becomes 8xy minus negative 2 times x squared minus y squared. So that's plus 2 times x squared minus y squared. Okay, so now we have x squared minus y squared, which we can factor out of the whole thing. And then we have minus 5 times 4x minus 20x squared plus, so we get 16xy plus 4x squared minus 4y squared. Okay. And so simplifying this becomes, well, first of all, this can factor to x plus y times x minus y. And this factors as, well, first let's simplify. So we have minus 16x squared plus 16xy minus 4y squared. So let's take out a minus sign. That won't affect things. So we have 16x squared minus 16xy plus 4y squared. And we can factor this as 4x minus 2y squared. Okay. And this, if you factor out a factor of 2, this is the same as 4 times 2x minus y squared. Okay, so looking at this resultant, we have exactly 4 factors, all right, corresponding to 4 points of intersection. One is x plus y, one is x minus y. Then we have multiplicity 2 at 2x minus y. And let's recall how we can interpret that. So the easiest one to interpret is the 2x minus y. So that corresponds to y equals 2x, which is the line that passes through this point of multiplicity 2. Okay, so this is the line y equals 2x. As for the lines y equals x and y equals minus x, those correspond to asymptotes. Okay, so as x and y approach infinity, you've got 2 asymptotes that both curves are approaching, and so at infinity, meaning in the projective plane, those intersect with multiplicity 1 along each of those asymptotes. Okay? I think that's pretty cool. Okay, we'll do one more example before moving on to moving towards Pappus. So we have 2 curves here. Let's name them. This will be C, and this will be D. Surprise, surprise. And we'll draw C. That's the standard circle. Radius 1 at the origin. And then we can draw D. That's the same, except shifted up 1. Okay? So what are the intersection points in this setup? Well, we can see right away we have at least 2, and they don't appear to be tangent. So it looks like we have, 2 intersection points of multiplicity 1. Okay, but Bézout says there should be 4, right? Again, these are 2 degree 2 curves. So where will these intersection points be? Well, they could be in the projective plane somewhere, or it could be complex intersection points. So let's figure out what it is exactly. So we're going to use the same tool as before. We're going to homogenize and then solve using resultants. So we have x squared plus y squared equals z squared. And then x squared plus y minus z squared equals z squared. Okay? So this translates to the same equation, x squared plus y squared minus z squared equals 0. And this, when we expand, gives us x squared plus y squared minus 2yz plus z squared equals z squared. And when we subtract, these 2 cancel. Okay? So now when it comes to z, this is degree 2 and this is degree 1. So when we're building the resultant, let's say this is C and this is D. For resultant with respect to Z of the polynomials corresponding to C and D, we'll need a 3 by 3 matrix. Okay? So the degree 2 curve we can put on the top line. So we get minus 1 corresponding to the coefficient of Z squared. There's no degree 1 Z term. And then we get x squared plus y squared. And as for the second equation, we have the degree 1 term is minus 2y times z, and the degree 0 term is x squared plus y squared. And similarly, minus 2y x squared plus y squared, 0, 0. Okay. We can compute this directly by expanding along one of these. Let's take the first row. We get minus 1 times the determinant of this 2 by 2 is just the square of x squared plus y squared. And then we have plus x squared plus y squared times the determinant of this 2 by 2, which is negative 2y squared. Okay. So that's going to be equal to, well, we can factor out an x squared plus y squared. That makes things easier. And then we're left with x squared plus, or rather, minus x squared minus y squared. And then we have plus 4y squared. Okay. So let's take this to the next page. If we were working over the real numbers, we might sadly be done. Because we're working over the complex numbers, x squared plus y squared factors as x plus iy times x minus iy. Okay, and meanwhile this, so we have 3y squared minus x squared. Okay, and that becomes, well, this stays the same. And this becomes y root 3 plus x times y root 3 minus x. Let's take this factored polynomial and translate each of the factors into a solution of these two equations, an intersection of these two curves. So the more basic equation here is this one, x squared plus y squared minus 2yz equals 0. So let's take that. And then plug in whatever information we have. So suppose this first factor was 0, so we would have x plus iy equals 0, so that means that x is equal to minus iy. Then that means x squared plus, so x squared is equal to minus y squared plus y squared minus 2yz equals 0. Okay, well then these y squareds cancel, and we're left with minus 2yz equals 0. So either y is 0 or z is 0. Okay, well if y is 0, then that means that x is 0, because x is minus I times y. And that means that z would have to be 1. But then looking at the other equation, x squared plus y squared equals z squared, this is going to be false. So that tells me that this has to be false. And instead we conclude z equals 0, which tells me that our solution point corresponding to 1 is going to be, let's take, so z is 0. Well, we can fix y to be 1, and then I is minus I, sorry, x is minus I, and that's a solution point. Okay, much the same deduction gives me that for the second factor, we have x equals positive iy, and our corresponding solution will be positive I times 1, positive I, 1, 0. Okay, as for the next factors, so we have y root 3 plus x equals 0. That means that x is equal to minus y root 3. Okay, so let's plug that into our equation here, x squared plus y squared minus 2yz equals 0. So we have x squared is 3y squared plus y squared minus 2yz equals 0. So now we have 4y squared minus 2yz equals 0, and we can factor this as 2y times 2y minus z equals 0. Okay, so again, two things are possible. Either y equals 0, but then again we have x and y will be equal to 0, and that means that z has to be equal to 1 because of the rules of projective geometry, but that would mean that x squared plus y squared is not equal to z squared, contradicting our equations, so we conclude that this is not possible. Instead, we say 2y minus z equals 0, and that gives us the following solution. We'll start with z. Z is going to be 1, then y will be a half, and x will be minus root 3 over 2. Okay? And if we look back at our graph, this is exactly minus root 3 over 2 and a half. Okay? And you can guess that the other answer is going to be positive root 3 over 2 and a half. Okay? And indeed it is. Okay, so some of our points we lose because of projective geometry, some of the points we lose because of complex numbers, but Bézout tells us exactly how many points we're missing and where to look for them. Okay, and now we're going to use Bézout's theorem to prove a beautiful theorem in geometry that was discovered by Blaise Pascal, a French mathematician. And the theorem goes as follows. Given 6 points, a, b, c, and a prime, b prime, c prime on a conic. Okay, so let's draw a conic so that we know what we're talking about here. Okay, so we've got, let's make it blue. Okay, so we've got an ellipse here. And now we're going to have 6 points. This will be A, B, and C, and we'll make another few points. We have A prime, B prime, and C prime. And then we connect them using 6 lines. Okay, so we connect A to B prime and C prime. I'm going to get a line here. B goes to A prime and C prime. C goes to A prime and B prime. Okay, and Bézout's theorem is this lovely, let me see if I can get like a dotted line. Oh no, I don't think so, but I'll make it pink. This lovely theorem which says that these 3 intersection points have to be all on the same line. Let's make it like that. That these 3 are collinear. Okay? And there's no, any 2 points lie on a line, but to say that 3 points generated in this unusual way have to lie on a line is a very surprising conclusion to come to. So how can we prove this? Especially, how can we prove this using Bézout? It seems like such a classical geometry type result, whereas Bézout is more about algebra and equations. So let's prove it. The idea is as follows. Okay, so let's take an example just to illustrate. So we have our conic. Let's call this conic X. Okay, and then we have our points. So we'll take A, B, C, and A prime, B prime, C prime. Okay, so now we're going to split up our lines into two groups. Okay, we're going to take, oops. So this will be one group, and this will be, let's get light blue. This will be another group. Okay. Now, we've been thinking about Bézout as describing curves, usually smooth curves, but it works just as well for equations that could be defined as products of other polynomials. So for instance, the equation describing the light blue lines, I can write that as the product of the three linear equations describing each of the lines. Okay? So light blue is described by a degree 3 polynomial. Okay, so it's described by some set of 3 linear polynomials. Okay? Okay, because if taking any point on any one of those 3 lines, it causes one of those factors to be 0, which means all 3 go to 0. Okay? So this is degree 3. Okay? Similarly, orange is also degree 3. Okay? And where do orange and blue intersect? Let's get a fresh color. I'll take some black. Here we go. Orange and blue intersect here, 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 but also at all of the green and red points. Okay, so that's 9 black intersection points. Okay, so Bézout's theorem tells us that should be it. There shouldn't be any more intersection points between orange and blue. Okay, and while we're at it, let's write a polynomial describing each of these curves. P of xy will describe the light blue lines, and Q of xy will describe the orange lines. Okay, now anything that's not on these lines, the equation shouldn't vanish on. Okay, so for example, if I were to choose this point, let's call it T. Let's make it ST just so we're not confused. So this should not, if you were to plug S and T into P or Q, you should get something that's non-zero. Okay, so in particular, okay. So what can I do? Well, let's say this is equal to A and that this is equal to B. Well, now I'm going to define a new polynomial. I'm going to call this f. F of xy is going to be equal to B times P of xy minus A times Q of xy. Okay. Let's borrow this. So I already know a few things about f. So I know that this is degree 3. because P and Q are both degree 3. I know that it includes all 9 black points because both P and Q are 0 there. So meaning that the set where f of xy equals 0 includes all 9 black points. And also, it includes ST. Okay. Well, now we run into trouble, okay, because we have this polynomial f. So f of xy equals 0 is a curve, and it's a degree 3 curve, and it's intersecting our conic. Well, it has all of, oh, shoot, it should be A, B, and C. It should have all of A, B, C, and A prime, B prime, C prime, but it also has ST. So it intersects the conic in 7 points. But what does Bézout tell us? It says that you have to multiply the degrees together. There should be only 6 points. Okay, so there's a contradiction here. It must be that the hypotheses of Bézout's theorem are not satisfied. The hypotheses of Bézout's theorem are not satisfied. Okay, and which hypothesis can we conclude that is violated? In particular, the curve f of xy equals 0 and the conic must have a common component. But the conic is just a conic, so that must mean that the degree 2 equation defining the conic divides f. Okay, so let's call that equation g. So g of xy defining the conic x must divide f. But in order, so that means that f equals g times some other polynomial, but since g has degree 2 and f has degree 3, this has to be a linear polynomial. Okay, g times L of, so this will be g of xy times L of xy, where that's linear. Okay. And since we know that there are an additional 3 points where f is 0, it must, and those aren't on the conic, they must all satisfy the same linear equation. We conclude that the 3 points where f of xy equals 0 not on the conic must all satisfy L of xy equals 0. And that proves Pascal's theorem. Okay. So that's that's relatively recent in France. Pardon me, I forget the century. But Pappus's theorem is an example of Pascal's theorem going all the way back to Greece. So if we have two lines, L1 and L2, and then we mark 3 points on each of them, and then you do the same cross lines as before. Oops. Okay, we're going to get the same magic line connecting all three of those intersection points as in Pascal's theorem. And the proof of this is very simple. A pair of lines is also a conic, and it's about that simple. And so you just have to apply Pascal's theorem. So through this incredible tool of Bézout's theorem, which brings with it so much cooperation between algebra and geometry and how to interpret equations as geometric objects in the proper way, we're able to deduce something that the Greek mathematicians, like Pappus, would have worked really hard to draw all sorts of diagrams to prove almost instantaneously. I think that's one of the beautiful things about mathematics, is that we're constantly having this dialogue between the mathematicians of the past and mathematicians of the present, constantly redeveloping, reframing ideas until we think we've got the right version. And that's especially true in the interplay between algebra and geometry. Thank you so much.